Okay, so good afternoon, and yeah, after some delay, we'll talk to you about our first result, an automated pipeline to retrieve high-resolution terrain models in support of Artemis exploration. So just a bit of context, if we are going back to the moon, we need a very accurate knowledge of lunar terrain topography, down to the meter, or even better than that, in order to ensure safe operations for rovers, astronauts, landers, but also to inform the choice of a landing site in terms of accessibility, power availability, and geological interest, and resource availability. And also a good knowledge of terrain topography also supports optical navigation in the approach to the landing site and CLIPS missions and operations. So in our work, we are using a technique called shade-from shading, along with images collected by the narrow-angle camera on board the Lunar Reconnaissance Orbiter, LRO, to enhance the resolution of altimetry-based low digital elevation models, LDEMs, in the following. So these models that you see here on the left in an example, and we use the information in the NAC images to introduce in these models local small-scale terrain features and topography down to 1 meter per pixel, which is the typical resolution of the NAC images. So our main goal is to set up a pipeline which automates most of the steps to pass from this DM to this DM. And to do this under the challenging illumination conditions typical of the lunar polar regions. So here is a schema of our current pipeline. And besides the actual computation of the DM, two very crucial steps are the image selection and the image alignment. So in terms of image selection, for computational reasons, we don't want to use all the images that we have overlapping the target region that we want to reconstruct. So we use machine learning based techniques and libraries to select a subset of images, optimizing the geographic coverage of the region, and also the sun illumination angles covering the region. And we evaluate our choice based on a set of indicators. Some of them are here on the right. For example, the number of images at each location in the target region with our chosen subset, the resolution, and also the spread of illumination angles provided by our choice of images. And this gives us also sets our expectations on the local quality of the resulting DM from our that we will get. So once we have a good subset of images that we have identified, we want to align them carefully among themselves and to the Lola terrain. Indeed, the imperfections in the orbits and pointing, especially computed for the LRO probe, can result in misalignments up to tens of meters at the surface, and the actual quality of the resulting terrain model is highly sensitive to these misalignments that need to be corrected. So this is quite a painful part of the processing that we are dealing with in several steps. First with a bundle adjustment, and then by refining the alignment between the images iteratively until these misalignments are not anymore, let's say, visible by human eye. So just as an example, here you can see on the left a maximum sunlit mosaic of around 20 images, 20 NAC images on an area of 1 kilometer by 1 kilometer. And the aliases that you can see here are caused by those misalignments among these 20 images that I was talking about. And if not corrected, these misalignments would result in critical artifacts and smooth slopes in the final elevation model. So we actually prefer to use the set of images here on the right, which has been corrected for alignment, and where you can see the very high level of detail provided by the NAC images. And this high level of detail is precisely what we want to use to enhance the LDEM, the LOLA DEM, which is our baseline and geodetic reference, and that you can see here for the same region as before in terms of an hillshade of the terrain and the slopes on the terrain. And I hope that at least in the zoomed region, you can see that there are gaps, smooth gaps, interpolated areas inside this terrain model between the altimeter tracks, the altimeter data tracks. And the high level of details in those NAC images that I was showing before is precisely what we want to use to fill these gaps. And thanks to our pipeline, we can pass from this terrain model to these, where these gaps are gone, and you can see details down to 1 or 2 meter per pixel. So yeah, you can see the improvement. Clearly, what we want is not only to generate a pretty model or pretty images. We want something which is reliable and to ensure safe operations and, in general, safe scientific exploitation of our models. So we systematically check our DEMs against the LOLA models for regional misalignments, as we have seen that such misalignments can easily cause tens of meters of vertical difference, of vertical errors, which we clearly don't want for most applications. But if everything is done correctly, then we really see that our SFS DEMs produce a significant improvement with respect to LDEM, as you can see here in these renderings when compared to an actual NAC image. And at the same time, they maintain the long wavelength agreement with LOLA. So once we are, our DM has been checked and we are happy with it, we distribute it as a standard set of products that you can see here, and which include both the DEM and ancillary products that can be directly used by the end user and also allow the end user to let's say propagate errors in his or her analysis and assess the local quality of the DEM for their use. And we we also produce additional products based on our DEMs, useful for both science and operations. So for example, here you would see, if I could run the videos, the rendering of illumination of both the LDEM and our DEM over a given time span, which is useful for many applications. So we're already using this pipeline to produce high quality terrain models around the South Pole, and we are continuously improving the reliability and the efficiency of our automated pipeline. Thank you for your attention.